Hey, hey, clearly, I am the sheriff of Astro Town, and I'd like to welcome you to this discussion on Cepheid variable stars, the type of stars that get bigger and smaller, and because of some interesting properties of them, we can use Cepheid variable stars to measure how far away some very far away things are, like other galaxies. Once people started getting awesome telescopes and they started looking at really distant stars, they noticed that some stars were doing some awesome things, like starting out small and then getting big and going back to small and then big. And so they were getting bigger and smaller. They were varying in their brightness. And if they made a graph of the apparent magnitude versus time, they would see it doing something like this. With up here, it is bright, and then down here, it was dim. And this was happening over the course of days, maybe anywhere from a week to a couple months. This was happening for different stars. And they found, if they looked at this graph enough, that it had a very regular period that seemed to never ever change. And different stars had different periods that they found. Only these Cepheid variable types. Now at first, Cepheid variables were just a novelty. Astronomers would have a party and they'd say, hey, let's look at the Cepheid variable, it's dim. And then they'd have another party next week and they'd say, whoa, now it's bright. But then someone got clever and they started making a graph of different variable stars, and they found out that there's a relationship between the different periods of all these different stars and how powerful they were. So you could, on this y-axis, put luminosity, or you could put absolute magnitude, and you could still get a relationship. Now notice it's not straight linear, it is a logarithmic type relationship. I can't spell logarithmic. That's misspelled, but take my word for it. It is logarithmic. Now, the even more awesome thing about Cepheids, besides just the novel fact that they do get bigger and smaller, is that they can be used to find the distance to distant galaxies, which is why we call them a standard candle. So let's say that step one of how to do this. First, you find your Cepheid. You need to look at a distant galaxy. Andromeda is kind of close, but let's say you were using that, and you found a Cepheid variable star that over the course of a few weeks was getting bigger and smaller. You then immediately high-five all of your astro buddies, because that is pretty awesome what you just did. You will have astronomy ladies all over you. Then you spend some time, probably weeks, measuring its average apparent magnitude, which is how bright it appears to you, which will be changing, and the period of time that it takes to go through the whole cycle. You write those down. Then, there's a well-known relationship between the period, which we're going to probably put on the x-axis of a graph, and the absolute magnitude, or the luminosity, which you'd probably put on the y, or there might be an equation that will allow you to calculate that absolute magnitude. And then, you will use some sort of relationship like this to compare its apparent magnitude, which you measured, absolute, which you calculated from the period, and then solve for distance. Here is a sample problem to use your new knowledge of the standard candleness of a Cepheid variable. Pause it, see what you can do to solve this. Hopefully, you looked at your graph and you got down to business, and one of the first things you should have done was estimate your period. And I estimated that to be about 53 days. You might be close to that, won't matter too much. Then you need to estimate your average apparent magnitude. And I estimated that to be about 25.0. I looked at the top, I looked at the bottom, and I took the average between them. You're done with the graph. You don't need it anymore, but hold on to that information, and you're going to use it to find absolute magnitude, because you now can use the equation that we wrote down before that says 2.78 times the log of that period. You plug in your 53 days and minus the 1.35. Plug that into your handy calculator and it'll spit out negative 6.1 as your absolute magnitude, which is quite bright. But for Cepheid variables, they are pretty massive stars compared to our sun, and so it makes sense that they're going to have a bright or negative absolute magnitude. Now, you have that, and you're going to use this hopefully familiar equation to you by now to find how far away it is, or its distance, in parsecs. So you'll plug in some values here. 25.0 minus a negative 6.1. Don't screw up your negative signs. And then you're going to end up with a plus 31.1 divided by 5 log of d over 10. You're going to do some fancy algebra, a 10 to the whatever power, and eventually you'll end up with a distance of about 1.7 times 10 to the 7th parsecs, which is crazy far. Turn that into megaparsecs, which is usually what we use for the distance to other galaxies, or light years, and we're going to end up with 17 megaparsecs, which is crazy far, and there's going to be a lot of uncertainty in this, but yeah, when something's 17 million parsecs away, you're going to make allowances for some uncertainty, and you're going to say to yourself, I am an awesome astronomer.